Hello, thank you for joining my presentation. Today I'm going to be talking about environmentally acceptable lubricants, hydraulic fluid performance under pressure. Before we get started, I would like to first introduce myself. My name is Bernie Roell, and I'm Vice President of Technology for RSC Bio Solutions. I have over 24 years of experience in the lubricant industry, from product development, product and technology management, to Vice President of Technology and Innovation for the Lubrizol Corporation, Ciba Specialty Chemicals, and Houghton International. I have a PhD in Organic Chemistry from Ohio University and a BS in Chemistry and a BA in Mathematics from Lock Haven University. For today's agenda, I'd first like to start out by talking about environmentally acceptable fluids and defining them for you. I would then like to review the definition of bulk modulus, and then we'll move into a bulk modulus data comparison of different fluids. We'll then talk about the effect of air entrainment and temperature on bulk modulus. We'll also look at the impact of bulk modulus on hydraulic fluids. Next, we'll go into a study where we compared 4 ISO 22 hydraulic fluids that are typically used in ultra-deep water applications, and we'll look at the relationship of viscosity versus pressure and temperature. And finally, we'll conclude with some observations. Let's first start by defining environmentally acceptable lubricants. If you look at the definition, according to the United States Environmental Protection Agency, a lubricant that is biodegradable, exhibits low toxicity to aquatic organisms, and has a low potential for bioaccumulations is considered an environmentally acceptable lubricant. Now, it's important that an environmentally acceptable fluid meet the requirements as defined by the U.S. EPA. However, it also needs to be proven, durable, and a worry-free lubricant for the consumer. We also need it to perform equivalent or better than mineral oil counterparts. The lubricant should meet the EPA and other local and global regulations. It should also meet corporate and environmental objectives and sustainability initiatives wherever possible. We also like environmentally acceptable fluids to be cost-effective and much safer products than the mineral oil counterparts. Now, before we get into our discussion about environmentally acceptable lubricants, I'd first like to define 4 groups of environmentally acceptable lubricants as defined per the ISO standard 6743 Part 4. As per ISO 6743 Part 4, we have hydraulic environmental triglycerides, otherwise known as HETG type fluids. The second class of fluids are hydraulic environmental polyalkylene glycols, HEPG. The third class is hydraulic environmental synthetic esters, HEES. And the fourth type is hydraulic environmental PAO and related products, HEPR. In today's presentation, I'm mainly going to be focused on the latter two, hydraulic environmental synthetic esters and hydraulic environmental PAO and related products, and comparing those to the mineral oil counterparts, petroleum-based, and a synthetic/mineral oil counterpart, also referred to as a partial synthetic. There are many problems and challenges facing our industry, in particular the cost, regulations, and potential fines associated with cleaning spills or leaks. Now more than ever, companies are looking for ways to help reduce the cost of spill remediation and the impact of spills on the communities and environments in which they operate. Hydraulic fluid leaks and spills are real and typically unplanned and sudden. Industry data shows that leaks far outpace catastrophic events. Hydraulic spills have to be reported and cleaned up. There are consequences of spills, and they vary on the type of fluid spilled into the environment. All spills result in lost productivity. However, some spills result in more costly fines and remediation, damage to the environment, and negative public relations. We see this in the waste industry when a garbage truck leaks hydraulic fluid in a neighborhood, on a golf course where a spill damages turf, or in the marine industry near waterways where oil leaks are harmful to plant and aquatic life. If we look at OEM hydraulic equipment trends, regulations are demanding use of EALs. Most recently, the EPA issued in December 19 of 2013 a vessel general permit mandating the use of environmentally acceptable lubricants in all oil-to-water interfaces. We're also seeing a trend in hydraulic equipment where pumps are operating at higher pressures, greater than 5,000 psi. We're also seeing reduced system sizes, which will cause the fluid to run hotter, which reduces flow losses in pumps and actuators, smaller sum sizes, and faster cycle times. So if we look at fluids, and we go back to our Fluid Dynamics 101 class, we're all taught that fluids are not compressible. But in fact, yes, fluids do compress at high enough pressure. And we measure the compressibility of a fluid by its bulk modulus of elasticity. This next slide shows that the material property characterizing the compressibility of a fluid is really how easy a unit of fluid volume can be changed when changing the pressure working upon it. This is what defines bulk modulus of elasticity. So in this example on this slide, air is 10,000 times more compressible than mineral oil. The next slide shows the equation for bulk modulus elasticity, where dP is the differential change in pressure on the object, dV is the differential change in volume of the object, and V is equal to the initial volume of the object. An increase in the pressure will decrease the volume. On the next slide, compressibility of the fluid in the numbers from the equation from the previous slide show that the higher the bulk modulus number, the less compressible the fluid. If we look at the bulk modulus data of different fluids, a large bulk modulus indicates a relative incompressible fluid. In this table, I've listed a number of common fluids in the industry. And if you look at the table, acetones, bulk modulus 0.92 would indicate that it would be the most compressible of the fluids listed in this table. And if you look at the paraffin oil or the SAE 30 oil, they have a bulk modulus of around 1.5 to 1.7. Water bulk modulus is 2.15. And as you move down the chart, you'll see that water glycols or glycerin have a much higher bulk modulus, 3.4, 4.35. And finally, on this scale, we show mercury with a bulk modulus of 28.5, which means it's very incompressible. In this presentation, we're going to focus more in on paraffin oil types with bulk modulus data in the 1.5 to 1.6 range. So as I mentioned in the agenda, we were going to talk about the bulk modulus of 4 ISO 22 grade hydraulic fluids typically used in ultra deep water applications. In this particular study, we looked at a petroleum-based fluid, a semi-synthetic petroleum, a synthetic ester environmentally acceptable type lubricant, and a synthetic biopolymer HEPR type. And we looked at the bulk modulus data at 3 different temperatures, 0 degrees C, 40 degrees C, 80 degrees C. And we also looked at the impact of temperature versus pressure at atmospheric pressure, which would be 0 megapascals. And we also looked at it at 68.95 megapascals, which would be approximately 10,000 psi. So from this table, you can see that the bulk modulus data at 0 degrees C is much higher than the data that we observed at 40 degrees C or 80 degrees C for all 4 of the fluids. If you look at the observations from that table that I just presented, at low temperature, 0 degrees C bulk modulus increase for both pressures for all 4 fluids compared to 40 degrees C and 80 degrees C. At high temperature, 80 degrees C bulk modulus decrease for both pressures for all 4 fluids compared to the 40 degrees C and the 0 degrees C values. Approximately 24% decrease in bulk modulus from 0 degrees C to 80 degrees C at 68.95 megapascals. And really, the data showed that the bulk modulus data does not differentiate between these fluids across all temperatures and pressures as much as we would have liked to have seen. If we look at bulk modulus versus percent air entrainment and temperature for a mineral oil-based fluid, this slide shows, in a study done in 2000 by George Totten, that if you look at the blue bars on this graph, 0% air, that raising the temperature 100 degrees F reduces the bulk modulus approximately 61% of its original room temperature value. Hence, increasing the temperature makes the fluid more compressible. Now, if you look at introducing 1% air at 80 degree F, that would be the green bar on the slide shown here. This reduces the bulk modulus 55%, hence making it more compressible. And if you look at raising the temperature and introducing 1% air, this reduces the bulk modulus by 67%, hence making it more compressible. In real life, you're probably somewhere between 0.1% and 1% air entrainment in a fluid, and typically operating anywhere between 80 degree Fahrenheit and 180 degree Fahrenheit, depending on the application. So you can see there's a great impact on compressibility when you include temperature and air entrainment into the equation. So if we look at temperature versus bulk modulus in a closed system, the bulk modulus of a fluid increases as the pressure is increased. As temperature rises, fluids expand, creating more pressure, hence increasing the bulk modulus. Also, compressing slowly will allow heat to dissipate, improving the incompressibility of the fluid. Effects of fluid compression can be dramatic, certainly increase in viscosity as the pressure increases. As the viscosity increases, this will reduce system efficiency. It'll also have delayed responses in the hydraulic equipment, power loss, more energy required to move the fluid, reduced flow, and possible system starvation. So in addition to looking at the bulk modulus data, we also tested those 4 ISO 22 grade hydraulic fluids, looking at the relationship between pressure and dynamic viscosity. And again, we looked at an ISO 22 petroleum, an ISO 22 semi-synthetic petroleum, an ISO 22 synthetic ester biodegradable, and an ISO 22 synthetic biopolyolefin HEPR. In this study, we conducted using a test method developed by Scott Baer at the Georgia Institute of Technology. The equipment used to measure the viscosity of pressure was a high-pressure falling body viscometer. This method utilizes a cylindrical cylinder moving vertically within a cylinder at various temperatures and pressures to determine the dynamic viscosity of the test fluid. For the study at 0 degrees C temperature, measurements were conducted by Ken Harris, University of New Zealand. These next 2 slides actually show photos, courtesy of Scott Baer, of the instrument that was used. The slide on the left actually shows the pressure transducer, the pressure vessel, and the equipment used to monitor the pressure. The slide on the right shows the pressure vessel chamber, where the sample is put into and measured. On the next slide, this actually shows the pressure vessel with the cylindrical barrels, and depending on the viscosity of the fluid, you either use a hollow barrel, a solid barrel, or a cup barrel, along with the retention springs and the cylinder. The next several slides that we're going to be talking about are going to show line graphs and bar graphs of each of the 4 fluids we measured at the 4 different temperatures. The first slide shows the ISO 22 fluids at 80 degrees C, and the line graph here really doesn't differentiate between the fluids at atmospheric pressure. And then as the pressures increase to 10,000 psi or approximately 70 megapascals, we see a little bit of differentiation between the 4 fluids. If we look at the next slide, the bar graphs show the percent viscosity increase at 80 degrees C at the 0 atmospheres and 68.95 megapascals. And again, there was not much differentiation between the synthetic ester and the HEPR, and there was some differentiation in terms of viscosity increase between the semi-synthetic and the petroleum fluid. If we look at the ISO 22 fluids at 40 degrees C, we can see, again, not much differentiation at atmospheric pressure and a little bit more separation between the 4 fluids at the higher pressures, with the HEPR having the least amount of change between 0 and 68.95 megapascals. The bar graph again shows about the same percent viscosity increase between the synthetic ester and the HEPR, and about a 50% difference between the semi-synthetic and the petroleum. If we look at the 4 ISO 22 fluids at 21 degrees C, this is where, as you begin to lower the temperature, you see the real impact and benefit of the HEPR ISO 22. At the higher pressure, you could see that it's clearly separated from the synthetic ester ISO 22, the semi-synthetic, and the petroleum. The data in the bar graph also shows about 100% difference in percent viscosity increase between the semi-synthetic and the petroleum versus the HEPR, and about a 50% viscosity increase difference between the synthetic ester and the HEPR. Finally, if we look at the ISO 22 fluids at 0 degrees C, we can see that there's a dramatic difference between the HEPR ISO 22 and the other 3 fluids in this line graph at the higher pressure. If we look at the bar graph, we can see that there's a dramatic difference between the HEPR and the 3 other fluids, 50% viscosity increase in the other 3 fluids versus the HEPR. If we look at the observations in those slides that I just described, low pressure, all 4 fluids look similar across all temperature ranges. At high temperature, 80 degrees C, all 4 look similar across all pressures. At mid-temperature, 40 degrees C, the ester and HEPR look the same, and the semi-synthetic and petroleum gain significant viscosity. At 21 degrees Celsius, the semi-synthetic, petroleum, and ester increase viscosity at a faster rate relative to the HEPR. At the lowest temperature, 0 degrees C, the ester increases viscosity at a faster rate relative to the HEPR, and the HEPR is clearly less impacted at higher pressure at 0 degrees C than the other 3 fluids. In conclusion, bulk modulus can affect power response, time, and stability. It can be controlled by fluid type, temperature, and air. It was clearly shown that pressure viscosity measurements further demonstrate that differences between fluids with similar secant bulk modulus under pressure at constant temperature can be differentiated using dynamic viscosity. I would like to acknowledge my RSC Bio Solutions team, Mark Miller, Rolf Geibach, Tyler Kutcha, and Andy Doyle. I'd also like to thank Scott Baer and Ken Harris for their contributions in doing the test work. And I'd like to thank you for your attention.